Okay, now we review question 19 as an application or an example where we apply these ideas we've already had a discussion on in a physics situation. I will do part A of the problem in order to keep the videos short. So in this video, in this case, in this problem, we're given the acceleration of a particle moving only in the xy plane, which is horizontal. This already gives us a hint that our problem is two-dimensional, and our acceleration is given by this vector. Note that this vector depends on t, that is time. So we have to realize that this particle undergoing this motion has a varying acceleration. Okay, so we're given that this particle, when time is equal to 0 seconds, it is located at 20 meters I hat and 40 meters j hat. And we're also given that its velocity at that instant is 5 meters per second in the x and 2 meters per second in the j. Now they ask us of what is the position of such a particle when time is 4 seconds. Okay, we give an acceleration and we are to find the position. You might recall the relationship, how to go from acceleration to the position vector. So if you're given the acceleration function, you can obtain first the velocity. This is going to be our detour, by performing the time integral of the acceleration, and doing so one more time will give you the position vector. So let's start. Our acceleration vector is given by 3t I hat. I should say let's do the integral of this for t j hat, and all of this should be integrated with respect to our variable t. This will give us our velocity vector. This will give us our velocity vector as a function of time. So let's actually do the integral. Okay, this first term, if we perform the integral, we're going to obtain something like 3t squared over 2. Of course, because we have to be as general as possible, we must include a constant. And our constant I will signify with c sub x. And this will make up our I hat component. Let's carry out the same procedure in the y component. We will end up with 4 over 2 t squared plus c sub y, and this will make up our j hat component. So we would effectively have our our velocity function. Okay, notice here what they've given us. They have given us a restriction that the velocity vector we obtain, it has to satisfy a condition, and this condition is that when t is equal to 0, this velocity vector we obtained must reduce to 5 in the I hat and 2 in the j hat. So let's go ahead and substitute t equals to 0 here and see what we obtain. Okay, if we were to do so and find v of 0 in this case, you will notice that we will have cx I hat and cy j hat. But we have been strictly limited to that this must be equal to 5 I hat and 2 j hat. This basically imposes conditions on cy and cx. This means cx must be equal to 5 and cy must be equal to 2. That means now we can adjust our velocity vector, which we obtained over here, with this new information. So let me put down the information. We have that cx ought to be 5 and cy ought to be 2. What this means is that vector function, the velocity function we have here must be given by this. Plus 5 I hat plus 2 t squared plus 2j hat. Remember, our goal was not to obtain the velocity function. Actually, our goal was to find the position function. So we still have a bit of work to do, and that work is basically performing the integral one more time. And here we are. We know that this shall be true. That is the integral of v bar of t dt. And obviously carrying this integral out means we will have 3t cubed over 2 times 3. Maybe let me put parentheses like that. And plus, now we need to integrate the second term of our x component. Well, over here we don't have a t, but we can introduce a t with a power 0, which would effectively mean our integral is going to be given by 5t. And as we had done before, we have to introduce a constant. In this case, I will call my constant d sub x. Now, over here we have concluded our I hat component. Of course, we could clean things up and cancel out the 3's over there, but that's just to make things nice. Primarily, I would like to conclude the second part. So here we go. Let's carry out the integral this time of the y component. This will look like 2 over 3t cubed plus 2t plus dy. And if you were to review my discussion of how I obtained each term on the x, you should be clear of how I obtained this one. Again, we were given strict stipulation that when time is equal to 0, not only must the velocity be given by that, there's another restriction that our position function must also reduce to that which is imposed over there. So let's perform that substitution in what we found over here. Let's substitute t equal to 0 here and see what that would mean for dx and dy. Okay, so if you were to simply substitute 0 for every time you run in a t, that would mean this term becomes 0 and so does that. That becomes 0 and so does that. So effectively what we're left with is d sub x I hat plus d sub y j hat. But remember, this must be equal to what they have given us there. 20 I hat and 40 j hat. What we learned therefore is that dx must be equal to 20 and dy must be equal to 40. Effectively then, let me put in some space. What that means for our position function, which we obtained over there, means we can substitute this information here. So dx is going to be 20, and dy is going to be 40 over here. So what we have is our position function as it depends on time is given by half t cubed plus 5t plus 20. This makes up our I component, and it's going to be 2/3 t cubed plus 2t plus 40. And this makes up our j hat component. Now we are in a good spot to respond to the rest of the questions. The rest of the questions are to find the position function or the position vector at 4 seconds. Now you simply need to substitute 4 for every time you run in a t in this expression. And the same, or once you have that vector in the instant time is equal to 4 seconds, you could find the direction of that using the regular procedure of performing the ratio of the adjacent side, which in our case it's going to be ry at 4 seconds and rx also at 4 seconds. And then you could find the arctan of that. You should be able to find both the vector itself and its magnitude over here. So this is going to be ry, rx again at 4 seconds. This is not for any general function, but any general time, but at a specific instance. Okay, that should be enough for this video. Hope that helps. See you in subsequent videos.